All right, on to 2.6 part 2. We're going to get a little bit more complex functions here, a little bit more interesting. Okay, we'll talk about domain, range, continuity, increasing, decreasing, all that stuff still holds, just that it's going to be a little bit more challenging. Okay, so the first thing we're talking about is piecewise functions. Now, piecewise functions, you know, we had all those basic functions that we had last time. Piecewise functions are just going to be different functions on different parts of the domain. Okay, and they're literally described to you in pieces, right? So here, if x, this is an example of a piecewise function. It's if x is less than 1, we have this function. But if x is greater than 1 or equal to 1, we have this function. Okay, and so all you do to find the domain and range of these things is that you graph those two functions, and you can indicate based on the two functions that we have what our domain and range are. So let's go ahead and do that. If x is less than 1, we have this function right here. Now you graph this function, right, with slope-intercept form. So you can go 0 to 4, that's your y-intercept, and then your slope is 2. So I can go down 2, 1, 2 over 1, down 2 over 1, down 2 over 1. Okay, so I don't actually want to go forward, right, because that 1 is going to change, but I can go up 2 over 1 more time and stop at 1. Okay. Now the thing is, I'm going to want an open circle here because at 1 it's actually this function and not this function. So we can graph this, and so it's going to be that line all the way if x is negative. But if x is positive, it's this line. Okay. And so now this line, the y-intercept, so it's the same thing as negative x plus 4, right? And so we'd start at 4, and then the slope is negative 1, and so we go down 1 over 1 right to here, and that would be filled in, right, because at 1 it is 1 3, that is the value. And then we just continue, so down 1 over 1, down 1 over 1, down 1 over 1, and so on. So this is actually our piecewise function right here. It's just these two functions defined in different ways. If you notice, you can define the domain, right? The domain is all real numbers because there's every number you can plug in. Notice there's a giant jump right here. It is not continuous on the entire domain because if we look right here, I can't draw this picture without picking up my pencil. Okay, so you can kind of do the same stuff we did last time. It's just that it looks a lot like the two functions that you're given. Okay, so let's go ahead and do one more. We have the function negative x minus 2, a line, right? If it's negative, and if it's positive, we have a parabola. Okay, so let's go ahead and graph this. It might just help to graph both things on a different piece of paper and transfer them over here. That would be fine as well. I'm just going to do it all on this one. Maybe we'll do it in 2 colors, though. Okay? So the top one we'll do in black. I'll put a little circle here. So it's negative 2 is our y-intercept, and we go down, right? But x is negative, and so we're going to go ahead and go up here. So up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. Right? It's the same slope as going down 1, right 1. Okay? And so we graph this line, and that is our left side, right? And we want it filled in at 0 because at 0 it is this function, okay? And so there's our line for the negative x, and for the positive x, we have x squared minus 2. Now that is just a parabola that we learned how to graph this back in Algebra 2, but it's pulled down 2, right? So it's going to be open circle right here, which you can't really see because it's not going to be defined there. But then we're going to have a parabola, so it's going to actually fill up. So if you plug in 1 to this, you would get 1 minus 2, which is negative 1. Plug in 2 to this, you would get 4 minus 2, which is 2, and so on. See this parabola. Okay, maybe graph one more point there. But we end up with this line over here, and then this parabola up there, okay? And that would be our equation of that one. So you're kind of just graphing both of those and then cutting it off wherever the domain tells you to, okay? So nothing too crazy there. You can have as many functions here as you want and as many broken up domains as you want. It can start to look super crazy. Very common form of giving a function, okay? Those are called piecewise functions. And now we're going to get on to kind of an interesting function. It's called the greatest integer function. I've also heard it called the ceiling function, and there's also a floor function. And I've also seen it in a different notation, which the book uses, which is double bracket. Okay, so if you see this in your book, that's what it's talking about. But what it does is it takes every number and it gives it the greatest integer that is either less than or equal to x. Okay. So for example, so this is actually the floor function if I was using the previous notation. But the idea is that no matter what, it rounds down. Okay? And so in this case, right, if you plug in like -2, the closest integer that is less than -2 is -2, right? We don't have to do that one. But -1.5, you round down, -2. 3 is 3. 3.99 is 3. Always round down. Okay? And so you actually end up with this cool little like line segmenty graph where it always rounds down no matter where you're at. Okay? And so it's filled in at the bottom of at the left side of the segment and always open on the right. Okay? And so for example, the greatest integer function of 2.5 is just 2. Okay? Hopefully that made a little bit of sense. So the domain here, is there any number that we cannot plug into this function? No, right? No matter what on here, even though there's a lot of discontinuities, there's always a spot that shows, like for example, 5. We can always find 5, right? It's going to be in this next little graph. So the domain is -infinity up to infinity. And the issue with the range, right? Notice we do not get every number. For example, we have no numbers between 1 and 2. Okay, so we're going to build a little set here. And it's going to be y line. This line is going to mean such that. So it's going to be all y values such that y is an integer. Okay? There's other ways to write this, but this is kind of nice. So we're going to have all the integers as our range, right? We can get negative or positive whole numbers. That's going to be our range. Okay? Now, it's constant on all the open intervals. Okay? So it's kind of important. It's not increasing or decreasing, but the open intervals is going to be like, for example, -2 to 1, -2 to -1, sorry, -1 to 0, 0 to 1, and so on, right? So you pick all these open intervals, it's going to be constant on there. It's never increasing, never decreasing, okay? So it's always just a flat line. And the last one, it is continuous. It's continuous within the little open intervals, but it's discontinuous. Discon, we're putting that. At all integer values in the domain. Okay, so anywhere that there is an integer in the real numbers, so for 2, 3, 4, there's always this jump that happens. Okay, so it's discontinuous at all the integer values. Okay, and so now we're going to practice graphing one of these. It's kind of interesting. Okay, so we have 1/3 x minus 2, a greatest integer function of that. Okay, so what we're gonna do is we're actually gonna make a table. We're gonna have a very similar graph to the one before, but let's make a table. So, let's do one of these. Here's x, here's y. Let's go ahead and plug in. I don't know. Let's plug in some different things. 0. Let's get where the let's do this. 0. Let's plug in 3. We'll plug in all the values of that. 0, 6, 9, -3, -6, -9. We'll do some other stuff. I kind of want 1 and 2 as well, but we'll see. Okay, this is a good start. We can do as many as we want though. Okay, you plug in 0 and you get -2. It rounds down to -2, right? You plug in 3 and you get 1 minus 2, which is -1. Plug in 6, so you get 2 minus 2, which is 0. Plug in 9, you get 3 minus 2, which is 1. Plug in -3, you get what? -1 minus 2, which is -3. Plug in -6, which is -2 minus 2, which is -4, and -9, which is going to be -3 minus 2 is -5. So those don't really help us that much, right? So I kind of want those intervals in a way here. I want to find out how big the interval is. And so let's go ahead and lock down. So we already have 0, but let's go with 1/2 and 1. See how big this interval actually is. Okay? So I plug in 1/2 and I get what? 1/6 minus 2? What is 1/6 minus 2? I don't know where I put my calculator at. There it is. So I get -1.8, which rounds down to -2. So it looks like that's still the same, right? I plug in 1, and I get 1/3 minus 2. So I get -1.6, which is still -2. Okay, let's plug in 1.5 as well. So 3 halves. I plug in 3 halves, and I get 2 minus 2, which is 0. So at that point, it's changed, right? At that point, it's changed. So it looks like it indicates that we end up with kind of a picture that looks to be from 0 up to 1, we have the same thing. But let me try 1 1/3. I feel like that's going to be something it tells us, okay? And we're just trial by error here. So 4/3, you plug that in. What do you end up with? 4/3 times 1/3 is 4/9 minus 2. So then we still get -2. Okay? So there's going to be a point when this stops happening. So it looks like it's suggesting for us that we end up with, plug in 0, we get -2. Plug in 1/2, we get -2. Plug in 1, we get -2. All the way up to here somewhere, right? How far negative can we go? If we plug in -1/2, that's when it goes away. So it looks like -1/3 maybe might be where it dies. So 1/9 negative minus 2. 1/9 negative minus 2. Yeah, so it kind of opens here and opens up at there, and we do that repeatedly. Okay, so from 0 up to 4/3 it's -2. From 4/3 up to 3 it's -1. So shuts here up to 3, and the third is going to be -1. It's going to kind of build this picture up and down. Okay, and so as far as the book's concerned, the most interesting way to graph this is just going to be to make ordered pairs, and you can kind of get an idea based on that. There's going to be all kinds of ways to do this, but again, your y values are still going to be integers, so your domain is going to be all real numbers. Your range is going to be any integer, and that's going to be fine. Okay, we might skip some integers. You just have to experiment a little bit. Okay, the book doesn't really give us any other ways of doing this other than making ordered pairs, so don't panic that this doesn't work. Okay, now the greatest integer function does have a name. It's not piecewise, but it's called a step function. Okay, it's called a step function for very obvious reasons, right? Let me find that last paper I had. I don't know where I put it, but look at this nicer graph. That's not my hand-drawn one. Do you see how it looks like a set of steps? Okay, nothing crazy there. Called the step function. Okay. All right, so let's apply that a little bit. So we have an express mail company charges $20 for a package weighing up to 2 pounds. For each additional pound or fraction of pound, there's an additional charge of $2. Okay, so it's 2 pounds plus whatever $2 up to that. So the function c of x represents the cost to send a package weighing x pounds. Y is c. Let's graph y equals c of x for x in the interval 0 to 6. Okay, and so for everything up in the interval, so let's set this out. For all x in 0 to 2, so that is sorry, I want to include 2. So up to 2 pounds, right? It's going to cost $20. So we have y equals $20. Now from x to 2 to 3, so from open interval from 2 to 3, we have y equals the original $20, right? Plus the $2 surcharge, so we get $22 for that, right? And now we keep this going. So for x in 3 up to 4, we add another $2, 24, and then it's going to be 26, and then it's going to be 28, and so on. Okay? And so now the graph is pretty easy to make, right? So if it's up from 0 up to 2, we have, I'm just going to kind of, so they do this squiggly line in the book too. That squiggly line means we're going to skip a bunch of stuff. Okay? So we're going to start right here at 20, and this is something that companies do all the time, right? We're going to kind of fluff this graph to make it look like we want it to. But we're squiggly line up to 20, and so it's 20 from open interval 0 up to 2. So open interval all the way up to 2, it's going to be 20. This should be flat. It looks a little bit up, but up to 2. Now from 2 to 3, okay, we'll squiggle in there. 2 to 3 is going to be 22. So open up to 3, and then 24 from 3 to 4, and so on. Okay? So we're going to have that. You should graph it from 0 to 6, I guess. That's what it says to do. So open, 24, 26. Okay? That would be our graph of that function. So nothing crazy there. But I mean, it's a super common way to do this, right? Just like phones are charged this way. It costs this much for your phone plan. Plus, if you do go over your data limit, for example, you get charged $10 per gig, right? This would be the graph of your charges in that as well. So not an uncommon way to graph different situations. Okay. I believe we're on to the last page for today, which is the relation x equals y squared. So this is a little bit different, right? Usually we have y equals x squared. Okay. So remember, a function is a relation. This might not be a word you've heard in a while, where every value in the domain is paired with one and only one range value. Okay? So that means that for every value in the domain, there's exactly one range value. You can't have more than one. Okay? So looking at this, we're going to have a little bit of an issue, right? Because this might not be a function. Okay? This isn't a function because we plug in 4 and we get this and this. We get two different range values. So one value in the domain is paired with two different range values, which is fine. Okay? But let's go ahead and graph this. It's going to be kind of interesting. So we have a relation, not a function. Okay? So we're going to go ahead and plot points from this, and we get some kind of nasty thing. So the domain here is going to be from 0 to infinity. Notice that there's no negative x values. So I want to include 0. And this is a very weird table, right? Because we don't have, there's two different y values for the same x value. It says it right there. Okay? And the range is going to be all real numbers, actually, because we're going to end up with everything that we want above and below. Okay? So these functions are often not very nice. And it's called a relation and not a function. Like I said, because each x value has exactly or it does not have exactly one y value. It has two y values, right? And so a common way to test this was the vertical line test you checked back in the day. If I put any vertical line on my picture, I'll use my pen to do that. If it touches the picture more than once, it's not a function. Okay? In this case, it touches it twice, which ruins its function aspect. But you can still draw them this way, okay? And that's very, very useful. It's still a relation. You can still graph it. You can still work with it. It's just not a function, okay? And that actually ends the section 2.6. If you have questions, reach out to your teacher. But otherwise, enjoy your day.